In this video, I'd like to show you how to perform some neutralization titration calculations. The term neutralization means that you're reacting an acid with a base, and they're in stoichiometric proportions, which means there will be no leftover acid or base. A titration occurs when you carefully measure the volume using an instrument called a burette. So let's see if we can illustrate this process by showing the mixture of an acid with a base. The neutralization of an Arrhenius acid with an Arrhenius base always produces a salt and water. For example, let's say you combined hydrochloric acid with the base sodium hydroxide. This reaction would produce the salt sodium chloride, and it would form water. Let's review how water is formed from acids and bases. The acid provides the H+ ion, while the base provides the OH-. Together, these combine to form HOH, or as it's more commonly written, H2O. Let's also review how salts are formed. A salt forms from a cation, in this case Na+, donated by the sodium hydroxide, and an anion, such as Cl-, which comes from our hydrochloric acid. Now, we'll combine these two processes in the chemical equation. Hydrochloric acid reacts with sodium hydroxide to form sodium chloride and water. And this is a neutralization reaction. Let's talk numbers now. If I had 10 moles of acid and reacted these with 10 moles of base, the two would run out at the same time, perfectly neutralizing each other. A look at the equation helps us understand why this is the case. You see, every 1 mole of acid will react with 1 mole of base. This produces a mole of salt and a mole of water. Now, what if I neutralize some hydrobromic acid with some calcium hydroxide? How would this neutralization process be different? Remember, the recipe for making water is to mix hydrogen ions with hydroxide ions, but I have 2 moles of hydroxide ions. So I'll need to have 2 moles of hydrogen ions, which must be provided by 2 HBRs. What we really see here is that there is a 2-to-1 ratio between the acid and the base. I need twice as many HBRs as CaOH2s. If I have 10 moles of calcium hydroxide, this will require 20 moles of hydrobromic acid to neutralize. Again, this is true because there are 2 OH- ions and only 1 H+ ion. So in our balanced equation, there's a 2 in front of the HBr, which allows us to make a mole of CaBr2 and 2 moles of water. A check of our equation should confirm that this is balanced. Let's look at one more example of an acid-base neutralization, this time between sulfuric acid, a diprotic acid, reacting with potassium hydroxide. So the equation would look like this. H2SO4 and KOH represent the acid and base. Now let's look at the numbers in this neutralization. Notice that the acid has 2 H+ ions to donate, but the base only has 1 OH- ion. It looks like I'll need twice as many moles of KOH to neutralize the H2SO4. Now, if I had 10 moles of acid, I would need to have twice as many moles of base to neutralize it. We'll see this ratio in the balanced equation. What salt do you think will form in this reaction? Correct. It's potassium sulfate. In addition, this reaction makes 2 moles of water. So here we have 3 different examples of neutralization reactions. Now, we're going to do some of the calculations that involve neutralization titration. these calculations are really just another type of stoichiometry problem. So let's review the stoichiometry strategy. Remember, in stoichiometry calculations, we always go from a known quantity to an unknown. And we learned that you can convert from grams, liters of a gas, or particles of a known into grams, liters, or particles of another substance in the reaction that we call the unknown quantity. To convert from moles to grams, we used a measurement called the molar mass. In addition, we added the concept of molarity to convert from moles of a substance to liters. Well, in neutralization titrations, we are going to try to find these two conversion factors to see if we can calculate the molarity, or the molar mass. To understand the strategy for finding these values, we should review what molar mass and molarity actually mean. Molar mass is a measurement of the grams per mole of a substance, while molarity is moles per liter. Let's do an example with one of these calculations. This problem says, when 20.0 milliliters of 0.25 molar HCl is titrated with 4.0 milliliters of NaOH, the solution is neutralized. What is the concentration of the base? Well, the first step to solving a stoichiometry problem is to write a balanced equation. Notice that we're reacting hydrochloric acid with sodium hydroxide, and an acid plus a base yields a salt plus water. The next thing I do when solving a stoichiometry problem is to write down what I know near the equation. For example, the problem says there are 20.0 milliliters of HCl, and I also see that the concentration of the HCl is 0.25 moles per liter. As I continue reading, I see that there are 4.0 milliliters of NaOH in this problem. And I see that I'm trying to find the concentration, or the molarity, of the NaOH. Now, for a shortcut, I see that molarity is measured in moles per liter, but that the volumes are in milliliters. I'm going to do a quick conversion of milliliters to liters by dividing by 1,000, or moving the decimal 3 places to the left. I'll do this for both milliliter measurements. So here's my strategy for solving this. I'm looking for molarity, or moles per liter, and that's the molarity of the base, or NaOH. This means I need the moles of sodium hydroxide and the liters of sodium hydroxide. From the problem, I see that I already know the liters of sodium hydroxide. So all I need is the moles of sodium hydroxide, and I can get these moles of sodium hydroxide from an abbreviated stoichiometry calculation. To get the molarity then, I'll begin with the liters of acid and convert this to moles of acid with the acid's molarity. Then I'll use the mole-to-mole ratio to find the moles of the unknown. At this point, I'll stop the stoichiometry calculation and plug the moles of unknown into the molarity formula. Let's give this a try. Yikes! Looks like I didn't balance my equation yet. No worries though, because this equation is balanced with all ones for the coefficients. Now I'll write the volume of the known solution, HCl, as 0.0200 liters. Then, I'll use the molarity to convert that volume into moles HCl. This allows me to cancel the liters of HCl. The molarity of HCl is 0.25 moles for every 1 liter. Next, I'll put in the mole ratio, converting from moles of known, HCl, to moles of unknown, NaOH. And that mole ratio is 1:1. This causes the moles HCl to cancel. So here I stop my calculation, which will give me the moles of NaOH. Multiplying 0.02 by 0.25 gives me 0.0050 moles of NaOH. This value will plug in here. So there are 0.005 moles for every 0.004 liters. Dividing these two numbers gives a result of 1.25 moles per liter. Well, that wasn't too difficult. Let's see if we can calculate the molar mass in our next example. Remember, the molar mass is measured in grams per mole. We'll again begin with the liters of the known solution. We'll use the molarity to convert liters into moles. Then, using the mole-to-mole ratio, we'll convert from moles of known to moles of unknown. And finally, we can plug in that number along with the grams of unknown to determine the molar mass. Let's give this a try. Example 2 reads, a 2.08 gram sample of unknown diprotic acid, H2A, is titrated with 45.11 milliliters of 2.00 molar NaOH. What is the molar mass of the acid? Now, just like before, I'd begin this calculation by writing out the balanced equation. The acid in this problem, which we don't know the formula for, we'll just call H2A. Don't worry about the symbol A. This just stands for some unknown anion. But you may be asking yourself, why are there two H's? Well, since the acid is diprotic, it has two H's to donate. This will react with sodium hydroxide, and an acid plus a base yields a salt plus water. In this reaction, the salt is made of Na and this unknown anion. Notice that the unknown anion A is actually a 2- ion. I can tell this because it's with two H+ ions. And just like with ionic compounds, the overall charge on an acid is always 0. So when I put sodium with the unknown anion, there will be two sodiums with each anion. The other product is water, but notice that there are two H's to react with the OH. This means I'm going to need two sodium hydroxides to provide enough OH to neutralize both of the H ions. And this will produce two waters. If you'd like, you can go back and make sure this equation is balanced correctly. Now, it's time to write down the data for our problem. The unknown diprotic acid has a mass of 2.08 grams, and the volume of the base is 45.11 milliliters. But just like before, I'll move the decimal 3 places to write this in liters. The concentration of this base is 2.00 m, or moles per liter. Finally, let's write down the units we're looking for, and that is the molar mass of H2A in grams per mole. So we're looking for a molar mass, which is in grams of H2A divided by the moles of H2A. And if we can do this calculation, we'll have the molar mass. And look, I've already got the grams of H2A. So all I need to find out is the moles of H2A. We'll do a calculation to find the moles of H2A. I'll begin with the volume of the known NaOH over 1. Next, I'll convert liters into moles using the molarity of the NaOH. This cancels the liters of NaOH. The number that goes in this step is written here and is 2.00 moles for 1 liter. Now remember, we're trying to find the moles of H2A, and we're getting closer. In fact, I just need to plug in a mole-to-mole ratio. Since the base was neutralizing a diprotic acid, it takes 2 moles of NaOH for every 1 mole of H2A. That's 2 moles NaOH and 1 mole H2A. Here, the moles of NaOH cancel, and we can calculate the moles of H2A. In addition, the 2's also cancel, leaving an answer of 0.04511 moles of H2A. Plugging this in the denominator here and dividing these two numbers, we can find the molar mass of the acid, which is 46.109510, etc. From the measurements, I see that there are only 3 significant digits, so I'll round my answer to 46.1 grams per mole. Now you can find molar mass and molarity from titration data. Good luck as you complete your titration calculations.